Section 1 Introduction. We're here to introduce our work, which is rooted in the recent advancements in deep learning, DL. Over the past few years, DL has made significant strides, especially in the areas of natural language processing and computer vision. Despite the differences in their applications, these advancements have a common thread. They all rely on large neural networks, often transformers, trained on massive datasets from the web using self-supervised learning techniques. This seemingly simple approach has led to the creation of highly effective large language models, LLMs, which can process and generate text with an impressive level of human-like proficiency. It has also given rise to vision transformers, VITs, which can extract meaningful information from images and videos without any supervision, and vision language models, VLMs, which can connect visual and language data, describing visual inputs in language or converting language descriptions into visual outputs. These models, due to their size and capabilities, have been dubbed foundation models, indicating their potential to serve as the base for various applications involving different types of input data. This brings us to our main question. Can we use the performance and capabilities of these vision language models to create more efficient and versatile reinforcement learning agents? After training on vast amounts of textual and visual data from the web, these models have shown signs of common sense reasoning, the ability to propose and sequence subgoals, visual understanding, and other key features. These are all crucial traits for agents that need to interact with and learn from their environments, but they can take an impractical amount of time to develop from scratch through trial and error. By utilizing the knowledge embedded in foundation models, we can significantly speed up this process. Inspired by this idea, we've developed a framework that places language at the heart of a reinforcement learning robotic agent, especially when it comes to learning from scratch. Our main contribution and discovery is this. We found that this framework, which uses LLMs and VLMs, can address several fundamental challenges in reinforcement learning settings. These include 1. Efficiently exploring environments with sparse rewards, 2. Reusing collected data to accelerate the learning of new tasks sequentially, 3. Scheduling learned skills to solve new tasks, and 4. Learning from observing expert agents. In recent studies, these tasks required different, specially designed algorithms to be addressed individually. However, we've shown that the capabilities of foundation models open up the possibility of a more unified approach. Section Summary. The recent success of large neural networks, such as transformers, trained on massive datasets using self-supervised learning methods, has led to the development of highly effective large language models, LLMs, and vision transformers, VITs. These models, known as foundation models, have the potential to be used as the backbone for various applications involving different input modalities. By leveraging the capabilities of foundation models, we propose a framework that uses language to improve the efficiency and generality of reinforcement learning agents, addressing problems such as exploring sparse reward environments, learning new tasks sequentially, scheduling learned skills, and learning from expert agents. Section 2 Related work. In recent years, we've seen significant advancements in the field of language models, LMs, and vision language models, VLMs, particularly in their ability to handle large and diverse datasets. These advancements have opened up new possibilities for their application, especially in the creation of agents that interact with the world. Previous research has combined LMs and VLMs with reinforcement learning, RL, agents in simulated environments. However, these approaches typically require a large amount of demonstration data for training. Our focus, on the other hand, is on developing RL agents from scratch, using LMs and VLMs to speed up the process. There has also been research into using LMs and VLMs in robotics. For instance, LMs have been used to plan subgoals in long horizon tasks, while VLMs have been used for scene understanding and summarization. These subgoals can then be translated into actions through language conditioned policies. While much of this research has focused on applying already learned skills in real-world settings, our work is centered on an RL system that learns these behaviors from scratch. We aim to highlight the benefits that these models bring to exploration, transfer, and experience reuse. Various methods have been proposed to handle tasks with sparse rewards, including curriculum learning, intrinsic motivation, and hierarchical decomposition. We show how LMs can create learning curriculums without any additional learning or fine-tuning, and how VLMs can automatically provide rewards for these subgoals, significantly improving learning speed. Previous research has also explored the reuse of large datasets of robotic experience by learning a reward model for new tasks. However, this approach often requires a large number of human annotations of desired rewards for each new task. In contrast, we demonstrate successful relabeling of past experience using VLMs, which can be fine-tuned with a small amount of data from the target domain. Our work is most similar to a method that uses LMs and VLMs to learn sparse reward tasks in Minecraft. However, there are some key differences. While they use a large internet dataset of videos, posts, and tutorials to fine-tune their models, we show that it's possible to effectively fine-tune a VLM with as few as 1,000 data points, and use off-the-shelf LMs. Additionally, we also explore how this framework can be used for data reuse and transfer, and learning from observation, in addition to exploration and skills scheduling. This represents a more unified approach to some of the core challenges in reinforcement learning. Section Summary. Previous work has explored the use of language and vision language models, LLMs and VLMs, in combination with RL agents in simulated environments, relying on large amounts of demonstrations for training. Our work, however, focuses on learning RL agents from scratch and utilizes LLMs and VLMs to accelerate progress. We demonstrate how LLMs can generate learning curriculums and VLMs can provide rewards for subgoals, improving learning speed without the need for additional annotations or fine-tuning. Additionally, we investigate data reuse, transfer learning, learning from observation, and exploration, offering a more comprehensive approach to reinforcement learning challenges. Section 3 Preliminaries. We're using a simulated robotic environment, based on the model by Lee et al., for our experiments. This environment includes a robot arm that interacts with 3 objects, red, blue, and green, placed in a basket. We've structured this as a Markov decision process, MDP, where the state space represents the 3D positions of the objects and the robot's end effector. The robot is controlled by specifying an x, y position, which it reaches using known inverse kinematics. The robot can either pick up or place an object. The observation space consists of images from 2 cameras fixed to the basket's edges. These images are 128 by 128 by 3 RGB images. The robot is given a task to complete, described in language form. The task could be to stack one object on top of another, or to stack all 3 objects. If the robot successfully completes the task, it receives a reward of +1, otherwise, it gets a reward of 0. We measure the difficulty of a task by the average number of steps needed to complete it when the robot is performing random actions. For example, stacking 2 objects has a difficulty of 10 to the power of 3, but an optimal policy could complete the task in just 2 steps. Stacking all 3 objects is even more difficult, with a difficulty of more than 10 to the power of 6, but an optimal policy could complete the task in 4 steps. Our goal is to use foundation models, which are pre-trained on large image and text datasets, to create a more versatile robotic agent. We've developed a framework that enhances RL agents with the ability to use language models, LLMs, and visual language models, VLMs, to understand their environment, their task, and the actions they need to take, all through language. First, the agent needs to convert visual inputs into text descriptions. We use CLIP, a large VLM, to do this. CLIP consists of an image encoder and a text encoder, both of which output a 128-dimensional embedding vector. The agent feeds an image from the environment to the image encoder and a possible caption to the text encoder. We then calculate the dot product between the embedding vectors and consider the description correct if the result is larger than a certain threshold, 0.8 in our experiments. Next, we use an LLM to generate a set of subgoals for the robot to solve based on the task instruction. We use Flan T5, an LLM fine-tuned on datasets of language instructions. We found that it performed slightly better than LLMs not fine-tuned on instructions. Finally, the language goals provided by the LLMs are converted into actions using a language condition policy network. This network takes an embedding of the language subgoal and the state of the MDP at a certain time step as input, and outputs an action for the robot to execute at the next time step. Our agent learns from interaction with the environment through a method inspired by the collect and infer paradigm. During the collect phase, the agent interacts with the environment and collects data. After each episode, the agent uses the VLM to infer if any subgoals have been encountered in the collected data. If the episode ends with a reward, or if any reward is provided by the VLM, the agent stores the episode data until the reward time step in an experience buffer. During the infer phase, we train the policy through behavioral cloning on this experience buffer after each agent has completed an episode. The updated weights of the policy are then shared with all the distributed agents and the process repeats. Section Summary. In this section, the authors describe the preliminary details of their experiments. They use a simulated robotic environment with a robot arm interacting with objects in a basket. The environment is formalized as a Markov decision process, MDP, with state, action, observation, and task spaces. The authors also introduce their framework for language-centric agents, which combines visual inputs with language instructions using pre-trained models. They use CLIP to describe visual inputs in language form and FLON T5 to generate subgoals based on task instructions. These language goals are then grounded into actions using a language condition policy network. The agent learns through interaction with the environment using a collect and infer learning paradigm, where it collects data during the collect phase and trains its policy during the infer phase. Section 5: Applications and Results. In this section, we'll delve into the applications and results of our research. We've previously outlined the components of our framework, which uses language as the central element to address key challenges in reinforcement learning, RL. We'll now examine each of these aspects, including exploration, reusing past data, scheduling and reusing skills, and learning from observation. Let's start with exploration, specifically, generating a learning plan through language. RL can greatly benefit from well-designed, frequent rewards. However, such rewards are often scarce in real-world settings. Robotic agents need to learn a variety of tasks in complex environments, but creating frequent reward functions becomes increasingly difficult as the number of tasks increases. Therefore, efficient and broad exploration is crucial to overcome these challenges and scale RL. Over the years, numerous methods have been developed to explore environments with sparse rewards. Many of these methods suggest breaking down a long-term task into shorter, simpler tasks through a learning plan. However, these methods often need to learn how to break down tasks from scratch, which can slow down the overall learning process. We show how an RL agent using language learning models, LLMs, can benefit from a learning plan of text-based subgoals, generated without any previous interaction with the environment. To guide exploration, the agent gives the task description to the LLM, which then breaks down the task into shorter subgoals, effectively creating a learning plan. For instance, the LLM can break down the task, stack the red object on the blue object, into subgoals like, the robot is grasping the red object, and, the red object is on top of the blue object. The agent then chooses actions based on the task description. While the environment only provides a reward if the task is completed, the Vision Language Model, VLM, acts as an additional, less sparse reward model. It checks if any of the subgoals were achieved at any step, based on the observations collected during the episode and all the text-based subgoals proposed by the LLM. If an observation represents a completion state for a subgoal, the agent adds the sequence of states, observations, actions, and task descriptions to our experience buffer. This process is illustrated in figure, in the appendix. We tested our framework on tasks like stack X on Y and triple stack, and compared it to a baseline agent that learns only through environment rewards. The results clearly show that our method is significantly more efficient than the baseline on all tasks. Notably, our agent's learning curve quickly rises in the triple stack task, while the baseline agent has yet to receive a single reward due to the task sparseness. These results suggest an interesting point. We can compare the sparseness of the tasks with the number of steps needed to achieve a certain success rate. We also trained our method on the grasp the red object task, which is the easiest of the three, with a sparseness of around 10. Under our framework, the number of steps needed increases more slowly than the sparseness of the task. This is a significant finding, as the opposite is usually true in RL. This slower growth, facilitated by the increase in the number of subgoals proposed by the LLM as the task becomes sparser, suggests that our framework can handle even more difficult tasks and make them manageable, assuming subgoals can be found with a uniform-like distribution at any point during exploration. Moreover, unlike previous methods that require carefully designed intrinsic rewards or other exploration bonuses, our approach can directly use prior knowledge from LLMs and VLMs to create a meaningful learning plan for exploration. This paves the way for general agents that explore in a self-motivated way, even in environments with sparse rewards. Section Summary. The authors describe their framework for reinforcement learning, RL, that uses language as the core of the agent. They focus on 4 key challenges in RL: exploration, reusing past experience data, scheduling and reusing skills, and learning from observation. They demonstrate how their RL agent leverages language models to generate a curriculum of text subgoals, which helps guide exploration and overcome the challenges of sparse reward environments. The results show that their framework is substantially more efficient than a baseline agent that learns only through environment rewards, even in tasks with high sparseness. This suggests that their framework can scale to even harder tasks and make them tractable, while also leveraging prior knowledge from language models for exploration. Section 5.2 Extract and Transfer. Efficient sequential tasks learning by reusing offline data. In this section, we discuss how our agents can efficiently learn sequential tasks by reusing previously collected data. This is a crucial capability for scaling up reinforcement learning systems that learn from experience. Our agents should be able to learn a series of tasks over time, using the data they've already gathered to speed up learning on new tasks, rather than starting from scratch. While there have been recent proposals to adapt general-purpose offline datasets to new tasks, these methods often require time-consuming human annotations and learning of reward models. To demonstrate our approach, we train our agents on 3 tasks in sequence, stacking a red object on a blue one, a blue object on a green one, and a green object on a red one. We label these tasks as TR, B, TB, G, and TG, R respectively. The idea is straightforward. While trying to solve TR, B, for instance, the agent might have already solved related tasks like TB, G, or TG, R, either fully or partially. The agent should be able to use these examples when attempting to solve new tasks, so it doesn't have to start from scratch but can use all the exploration data gathered for previous tasks. Our agent collects an experience buffer of interaction data. We now provide the agent with 2 different buffers, a lifelong buffer, or offline buffer, where the agent stores each episode of interaction data and continues to expand at task. After task. Then, the agent has a new task buffer, which is reset at the beginning of each new task and filled with trajectories that result in a reward, either external or internally provided by the Verbal Language Model, VLM, using Linguistic Language Model, LLM, text subgoals. The policy network is optimized using the new task buffer. However, unlike before, while the first task, TR, B, is learned from scratch, the agent reuses the data collected during task N to speed up the learning of the next task, N+1. The LLM breaks down Tn+1 into text subgoals. The agent then extracts each stored episode N from the lifelong offline buffer. It then takes each episode's observation OT, N, and uses the VLM to compute a score between all image observations and all text subgoals. If the score is larger than a certain threshold, the agent adds all the episode's time steps up to T to the new task buffer. This procedure is repeated for each new task at the beginning of training. As a result, the agent doesn't start learning new tasks from scratch. At the beginning of task Tn, the current experience buffer is filled with episodes useful for learning the task extracted from T0, N. As N increases, the amount of data extracted from T0, N also increases, accelerating learning. We applied this method to learn TR, B, TB, G, and TG, R in succession. At the beginning of each new task, we reset the policy weights to investigate our framework's ability to extract and reuse data, thereby isolating and eliminating effects that could be due to network generalization. Our experiments clearly show the effectiveness of our technique in reusing data collected for previous tasks, improving the learning efficiency of new tasks. These results suggest that our framework can be used to enable lifelong learning capabilities in robotic agents. The more tasks are learned in succession, the faster the next one is learned. This can be particularly beneficial when deploying agents in open-ended environments, especially in the real world. By leveraging data across its lifetime, the agent should be able to learn new tasks much faster than learning purely from scratch. Section Summary. In this section, the authors propose a method for agents to learn a series of tasks over time by reusing previously collected data, rather than starting from scratch. They demonstrate this approach by training agents to sequentially stack objects of different colors. The agents extract relevant examples from their past experiences to bootstrap learning on new tasks, resulting in improved learning efficiency. The experiments show that this technique can unlock lifelong learning capabilities in robotic agents, enabling them to learn new tasks faster by leveraging data from previous tasks. Section 5.3 Scheduling and Reusing Learned Skills. In this section, we'll discuss how our system allows an AI agent to schedule and reuse learned skills, and how it can learn from observing others. Our system empowers the AI agent to explore and learn how to solve tasks that offer rewards infrequently. It also allows the agent to reuse and transfer data for continuous learning. Using a policy that's conditioned by language, the agent can learn a series of skills, which we'll refer to as M. These skills can be described as language goals, such as, the green object is on top of the red object, or, the robot is grasping the blue object. Our system enables the agent to schedule and reuse these M skills to solve new tasks that it hasn't encountered during training. The process is similar to what we've discussed in previous sections. A command like, stack the green object on top of the red object, or, stack the red on the blue and then the green on the red, is given to the Language Learning Model, LLM. The LLM then breaks down this command into a list of shorter goals. The agent can then translate these goals into actions using the policy network. When the agent is executing a skill, it checks at each step if the goal of the skill has been reached in the current observation. If the goal has been reached, the agent starts executing the next skill, unless the task is already solved. Learning from observation is a desirable ability for AI agents. Our system allows the agent to learn from watching a video of an expert performing a task. This enables the agent to learn from observation in a single attempt. In our tests, the agent watched a video of a human stacking objects. The video was divided into frames. The agent then used the video learning model, VLM, along with the textual description of the learned skills, to identify the sub-goals that the expert encountered during the task. The agent embeds each learned skill in each video frame and calculates the dot product between each pair. It then lists all the sub-goals that have a similarity greater than a certain threshold. This gives the agent a chronological list of the sub-goals that the expert encountered during the task. The agent then executes the list of sub-goals. Despite being fine-tuned only on images from the Mu-Jo-Co simulation, the VLM was able to accurately predict the correct text-image correspondences on real-world images showing either a robot or a human arm. Interestingly, we still refer to it as the robot in the captions, but the VLM generalizes to a human hand regardless. Section Summary. The framework described in this section allows the agent to efficiently explore and learn to solve tasks with sparse rewards, as well as reuse and transfer data for lifelong learning. By using a language condition policy, the agent can learn a series of skills and schedule and reuse them to solve new tasks. Additionally, the agent can learn from observing an expert through videos, where the video frames and textual descriptions of learned skills are used to detect and execute the sub-goals encountered by the expert.